Look up at the night sky, and what you see is barely a fraction of the colossal mystery surrounding us. The stars, the planets, even our entire Milky Way, they're just tiny specks in something far grander, the Virgo Supercluster. This sprawling web of galaxies, stretching over 110 million light-years, is our cosmic neighborhood, and it's teeming with secrets that defy explanation. From ghostly radio signals to galaxies that shouldn't exist, the Virgo Supercluster holds phenomena so bizarre, they challenge everything we think we know about the universe. And today, we're diving deep into 25 of its most mind-bending mysteries, enigmas that even the brightest scientists struggle to unravel. Picture this, a single supercluster, a gravitational tapestry weaving together thousands of galaxies, each with billions of stars, yet somehow, it's just one thread in the even larger fabric of the cosmos. Within this immense structure, strange forces are at work, forces we can't yet explain. Why do some galaxies spin in ways that break the laws of physics? What's behind the eerie voids where almost nothing exists? And perhaps most unsettling of all, why does it feel like something or someone might be hiding in the shadows of this vast expanse? The Virgo Supercluster isn't just a collection of celestial objects, it's a cosmic puzzle box waiting to be opened. This journey isn't just about listing strange phenomena, it's about stepping into the unknown, where every discovery raises more questions than answers. Some of these mysteries might hint at entirely new physics, while others could rewrite the story of our universe. And the most thrilling part, you don't need a telescope to join the adventure. All you need is that same spark of curiosity that's driven explorers, scientists, and dreamers for centuries. So, are you ready to uncover the secrets lurking in our cosmic backyard? Let's begin. The first mystery lurking in the Virgo Supercluster might be the most unsettling of all because it's invisible. Across countless galaxies, stars and planets whirl through space at speeds that shouldn't be possible. Based on the gravity of all the visible matter we can detect, these galaxies should be flying apart. Yet something unseen holds them together, an invisible hand gripping the cosmos. Scientists call this enigma the missing mass problem, and it's been haunting astronomers for decades. Take the Virgo cluster itself, a dense knot of over 1,000 galaxies at the heart of the supercluster. When researchers measure how these galaxies move, they find their velocities defy expectations. The visible stars and gas simply don't provide enough gravitational pull to explain their motion. So where's the extra mass coming from? The leading theory points to dark matter, an elusive substance that doesn't emit, absorb, or reflect light, making it completely undetectable with telescopes. Yet its gravitational influence is undeniable, warping the very fabric of space around it. But here's where things get even stranger. Despite decades of searching, no one has directly observed dark matter. Experiments deep underground, detectors in space, even the most powerful particle colliders all have come up empty. Some scientists argue we might be missing something fundamental, that our understanding of gravity itself could be flawed. Others propose exotic particles or hidden dimensions as possible explanations. The truth is, we're still grasping in the dark, quite literally. What makes this mystery so profound is its scale. Dark matter isn't just a quirk of the Virgo cluster, it's woven throughout the entire universe, outnumbering normal matter 5 to 1. Without it, galaxies wouldn't have formed, stars wouldn't shine, and we wouldn't be here to ponder its existence. Yet it remains one of the greatest unsolved puzzles in modern astrophysics, a ghostly presence shaping the cosmos while slipping through our fingers. And until we crack this mystery, a fundamental piece of our universe's story will stay hidden in the shadows. Now let's zoom in on a patch of the Virgo supercluster that makes astronomers scratch their heads, a place where galaxies seem to huddle together in a way that defies the odds. Known as the Virgo Overdensity, this region is packed with far more galaxies than probability alone would predict. It's as if the universe rolled a cosmic dice thousands of times and somehow kept landing on the same number. Think of the cosmos like a vast, bubbling soup with galaxies scattered somewhat evenly throughout. But in this one pocket, they're clumped together like dumplings crowding the ladle. The question is, why? Some researchers argue it could just be chance, a random fluctuation in the grand distribution of matter. But others suspect something deeper is at play, a hidden factor tugging galaxies into this peculiar arrangement. One striking observation is how these galaxies move. Unlike the predictable orbits we see elsewhere, their paths appear oddly synchronized, almost as if responding to an unseen conductor. Could this be another fingerprint of dark matter's influence, its gravity weaving an invisible scaffold that draws galaxies together? Or is there a more exotic force at work, something beyond our current models of cosmology? Then there's the sheer scale of the overdensity, spanning tens of millions of light years. It's not just a minor statistical blip. If this were purely random, the odds would be astronomically low, like flipping a coin 1,000 times and getting heads every single time. That improbability has led some scientists to propose alternative explanations, like remnants of ancient cosmic collisions or echoes from the universe's earliest moments when its structure was first imprinted. What makes this mystery particularly tantalizing is what it could reveal about how the universe builds itself. If the Virgo overdensity isn't a fluke, it might hint at unknown processes shaping cosmic architecture, processes we haven't even begun to map. Every time we think we understand the rules of galaxy formation, anomalies like this remind us how much is still waiting to be discovered. And until we solve it, this crowded corner of the supercluster will keep challenging our assumptions about the cosmos. Deep within the Virgo supercluster, an invisible force is pulling entire galaxies, including our own Milky Way, toward a point in space we can't even see clearly. This cosmic heavyweight, known as the Great Attractor, exerts a gravitational influence so immense that it bends the paths of galaxies across hundreds of millions of light years. Yet despite its power, pinpointing its exact source feels like trying to solve a puzzle with half the pieces missing, because our view is blocked by something called the zone of avoidance. Imagine the Milky Way as a sprawling city at night, its bright lights representing stars and dust. Now picture a thick fog bank rolling in, obscuring everything behind it. That's essentially what the zone of avoidance is, a dense region of gas, dust, and stars in our own galaxy's plane that blocks our view of the universe beyond. Right behind that fog sits the Great Attractor's likely home, hiding in plain sight. What we do know is terrifyingly intriguing. Measurements show galaxies streaming toward this region at speeds over 600 kilometers per second, as if caught in a celestial riptide. Early theories suggested a single massive object, perhaps a supercluster of galaxies, might be responsible. But when astronomers peered around the zone of avoidance using infrared and radio telescopes, they found something even more surprising. The Great Attractor isn't alone. It appears to be part of a far larger structure called the Laniakea Supercluster, a web of galaxies spanning 500 million light-years, with the Great Attractor acting as a gravitational anchor point. Here's where the plot thickens. The Great Attractor's pull isn't as strong as originally thought. It's merely the local manifestation of something even grander. Recent studies reveal most of the motion we observe comes from beyond it, likely due to an immense concentration of mass nicknamed the Shapley Attractor, located another 650 million light-years away. This suggests the Great Attractor might be more like a waypoint in a much longer cosmic journey, with Shapley as the ultimate destination, yet mysteries remain. Why does the Great Attractor's immediate region exhibit such unusual galaxy distributions? Some computer simulations suggest it could be a gravitational nexus, where multiple filamentary structures of the cosmic web intersect, creating a dense knot of dark matter and galaxies. Others propose its behavior might require modifications to our understanding of gravity on large scales. every workaround to study it, like using X-ray observations to map galaxy clusters hidden behind the Milky Way, brings new questions about what truly drives this colossal flow of galaxies. The implications are staggering. If the Great Attractor is just one piece of a larger gravitational puzzle, it means we're witnessing the universe's large-scale structure in motion, a dynamic dance choreographed by unseen mass. And until we develop new ways to peer through the zone of avoidance, this enigmatic force will keep pulling us both literally and scientifically toward answers just out of reach. Amid the bustling cosmic metropolis of the Virgo Supercluster, some of its most puzzling residents are barely visible ghostly islands of stars so faint they almost vanish against the blackness of space. These are ultra-diffuse galaxies, celestial specters with masses spread so thin, they defy everything we know about how galaxies survive in such a crowded environment. Picture a city with streetlights spaced miles apart, their glow barely piercing the darkness. That's the eerie reality of these cosmic anomalies, where stars drift so far from one another, their collective light is hundreds of times dimmer than our Milky Way. What's truly baffling isn't just their faintness, but their resilience. The Virgo cluster is a gravitational battlefield where galaxies routinely collide and tear each other apart. Yet somehow, these wispy structures endure, their delicate stars resisting the cluster's violent tides. It's like finding a cobweb intact in the middle of a hurricane, a phenomenon that shouldn't be possible. One leading theory suggests these galaxies are cloaked in protective halos of dark matter, their invisible scaffolding holding them together against the chaos. But when astronomers measured the motion of stars within them, the numbers didn't add up. Some appear to have surprisingly little dark matter at all, throwing that explanation into doubt. Then there's the mystery of their birth. Most galaxies in dense clusters like Virgo are stripped-down husks, their gas stolen by close encounters, leaving them barren and aging. Yet ultra-diffuse galaxies often float in quiet isolation, seemingly untouched by the violence around them. Some contain puzzling reservoirs of gas, as if they've somehow avoided billions of years of cosmic drama. Others sport bizarrely youthful blue stars, hinting at recent, unexplained bursts of star formation in regions where such activity should have long since ended. Perhaps the most striking example is Dragonfly 44, a ghostly giant in the Virgo cluster with the mass of the Milky Way but only 1% of its stars. This galaxy emits so little light, astronomers initially missed it entirely hidden in plain sight until advanced telescopes peeled back the darkness. Its existence challenges the very definition of a galaxy, forcing us to ask, how many more of these phantoms are lurking undetected, rewriting the rules of cosmic evolution? The deeper we look, the more questions arise. Could these galaxies be failed experiments of the universe, objects that never quite coalesced into typical spirals or ellipticals? Or are they the remnants of ancient collisions, their stars scattered like dust in the wind? Every new discovery peels back another layer of the mystery, revealing a cosmos far stranger than we ever imagined, one where the faintest whispers might hold the loudest secrets. In the Virgo Supercluster's grand cosmic tapestry, one discovery has sent shockwaves through astronomy galaxies that defy the most fundamental rule of cosmic architecture. Meet NGC 1052 DF2, a galaxy that shouldn't exist. Unlike its neighbors, this enigmatic structure appears to harbor little to no dark matter, the invisible glue thought to bind all galaxies together. Its existence isn't just puzzling. It's a direct challenge to everything we thought we knew about how galaxies form and survive. At first glance, NGC 1052 DF2 looks like any other ultra-diffuse galaxy, faint, sprawling, and ghostly. But when scientists measured the motion of its stars, expecting to find the telltale tug of dark matter, they got a result that left them stunned. The stars were moving far slower than predicted, suggesting the galaxy's mass was almost entirely accounted for by visible matter alone. It was as if someone had removed the scaffolding holding up a skyscraper, yet the building somehow remained standing. This discovery sparked immediate controversy. Dark matter has been the cornerstone of galaxy formation theory for decades, explaining why galaxies don't fly apart under their own rotation. Without it, NGC 1052 DF2 should have disintegrated long ago. Skeptics question the measurements, proposing alternative explanations. Perhaps hidden gas clouds or tidal forces from nearby galaxies were skewing the data. But follow-up observations only deepened the mystery. The galaxy's globular clusters, ancient groups of stars orbiting its outskirts, also moved at sluggish speeds, confirming the lack of dark matter's gravitational influence. Then came the real twist. NGC 1052 DF2 isn't alone. Other dark matter-deficient galaxies, like NGC 1052 DF4, were soon found lurking in the same cosmic neighborhood. Their existence raises a radical question. Could dark matter and galaxies exist independently of one another? Some theorists suggest these oddballs might be tidal dwarfs, born from violent collisions where gas was stripped away, leaving behind mostly stars. Others propose they're remnants of a primordial universe where dark matter wasn't evenly distributed, creating rare pockets where galaxies formed without it. But the implications go far beyond a handful of weird galaxies. If dark matter isn't always the invisible hand shaping cosmic structures, our entire framework for understanding the universe's evolution might need revising. Could there be two distinct paths to galaxy formation, one with dark matter, one without? And if so, what does that mean for the countless other galaxies we've studied under the assumption that dark matter is universal? Every new observation of these cosmic outliers chips away at our assumptions, revealing a universe far more unpredictable than we ever imagined. What makes this mystery especially tantalizing is its potential to rewrite the rules. Dark matter-free galaxies aren't just exceptions, they're cosmic counterexamples, forcing us to confront the gaps in our knowledge. As telescopes grow more powerful, searching for others like them could unlock clues about dark matter's true nature or reveal entirely new physics at work. For now, these ghostly rebels stand as a humbling reminder. Even in our own supercluster, the universe still holds cards it hasn't yet played. The Virgo Supercluster holds a cosmic anomaly so counterintuitive, it's been dubbed the Redshift Desert, a vast stretch of space where galaxies appear to vanish without explanation. Redshift, the stretching of light waves as objects move away from us, is astronomy's yardstick for measuring cosmic distances. Normally, galaxies are spread evenly across different redshifts, like rungs on a ladder marking the universe's expansion. But in the Virgo cluster, something disrupts this pattern, leaving conspicuous gaps where galaxies should be thriving. Imagine walking through a forest where entire sections of trees are missing, not fallen, not dead, just absent. That's the eerie reality astronomers face when mapping this region. Surveys reveal abrupt drop-offs in galaxy counts at specific redshift intervals, as if a cosmic sieve has filtered them out. The starkness of these voids contradicts predictions from the standard model of cosmology, which assumes matter distributes relatively uniformly over large scales. So why does Virgo's cosmic ledger show these unexpected blanks? One leading hypothesis points to the cluster's turbulent history. Virgo is a gravitational melting pot where galaxies collide, merge, and sometimes eject one another like celestial billiard balls. Computer simulations suggest violent interactions could have flung galaxies out of specific redshift bands, creating temporary voids. But critics argue this doesn't fully explain the desert scale. Some gaps span distances too vast for local dynamics alone to account for. Then there's the dark energy angle. This mysterious force accelerating the universe's expansion might influence how galaxies cluster on immense scales. Some theorists propose dark energy could suppress galaxy formation in certain regions, leaving behind these barren redshift stretches. Yet if true, why don't we see similar deserts elsewhere in the cosmos? The Virgo cluster's version seems peculiarly pronounced. Perhaps most intriguing are the alternative explanations that venture beyond mainstream physics. Could unknown quantum effects in the early universe have imprinted these gaps? Or might they be signatures of parallel universes brushing against our own? A far-out idea, but one that gains traction when conventional models fall short. Every telescope pointed at this enigma brings back data that challenges our assumptions. The Redshift Desert isn't just a curiosity, it's a potential Rosetta Stone for decoding cosmic evolution. If we can understand why galaxies avoid these zones, we might unlock secrets about dark matter's behavior, the universe's expansion rate, or even the validity of our foundational physics. Until then, these ghostly gaps stand as silent reminders of how much we still don't know about the cosmos's grand design. At the heart of the Virgo Supercluster lies one of the most energetic spectacles in the known universe, a monstrous black hole spewing a jet of plasma across 5,000 light-years at nearly the speed of light. This cosmic blowtorch originates from Messier 87, a giant elliptical galaxy whose supermassive black hole, weighing in at 6.5 billion solar masses, acts like a particle accelerator of unimaginable power. The jet's brilliance outshines the entire galaxy around it, visible across the electromagnetic spectrum from radio waves to gamma rays. Yet for all its ferocity, the mechanisms powering this relativistic beacon remain one of astrophysics' greatest puzzles. The physics at play here stretch our understanding to its limits. Black holes are notorious for their gravitational grip, so how does M87s eject material with such violence? Current theories suggest an intricate dance between the black hole's spin and its accretion disk, the swirling maelstrom of superheated gas and dust spiraling toward oblivion. Magnetic fields, twisted into coils by the black hole's rotation, might funnel some of this material outward along the poles rather than inward toward the event horizon. Think of it like water spiraling down a drain, only for a powerful pump to blast some back out through narrow hoses at either end, but the details refuse to cooperate. For starters, the jet maintains an extraordinarily narrow beam over vast distances, resisting the tendency to spread out. Even more baffling is its intermittent nature. The jet isn't a steady stream but erupts in bursts, with knots of plasma visibly moving outward at apparent speeds faster than light, an illusion caused by their near-light velocity angled toward us. These fluctuations suggest the black hole's feeding habits are far more erratic than models predict. Then there's the energy problem. The jet's output dwarfs what should be possible from accretion alone. Some researchers propose the black hole's spin acts as a battery, storing and releasing energy through processes we've only begun to theorize. Others speculate about quantum effects near the event horizon or even more exotic physics involving dark matter interactions. The Event Horizon Telescope's landmark image of M87's shadow in 2019 provided unprecedented data, yet instead of solving the mystery, it revealed finer details that complicate the picture further, like asymmetric emissions hinting at unseen turbulence in the magnetic fields. What makes this jet particularly tantalizing is its role as a cosmic laboratory. Similar structures exist throughout the universe, but M87's proximity, 55 million light-years, may seem distant, but cosmically speaking, it's our backyard gives us a front-row seat to study these processes in unparalleled detail. Every observation peels back another layer. X-ray telescopes catch the jet's particle collisions, radio arrays map its magnetic skeleton, and gravitational wave detectors may one day sense the ripples from the black hole's spin. The implications ripple outward. If we can decipher how M87's jet works, we might unlock secrets about galaxy evolution. These outflows likely regulate star formation by heating interstellar gas, or even practical insights for future plasma propulsion technologies. For now, this celestial firehose continues to defy easy explanation. a humbling reminder that even the most studied objects in our universe still guard their deepest secrets fiercely. Hidden within the chaos of the Virgo cluster is a cosmic mystery so geometrically perfect, it challenges our understanding of how the universe organizes itself, a vast ring of galaxies, each positioned like pearls on a necklace spanning over 10 million light-years. This celestial circle, known as the Virgo stellar stream, appears too precise to be random, yet its existence defies conventional models of galactic formation. The question tearing astronomers apart is simple. Is this elegant structure a real three-dimensional arrangement, or just a fleeting illusion created by our limited perspective? On one side of the debate are those who argue for projection, the idea that galaxies at different distances happen to align along our line of sight, creating a false ring. It's like holding up a handful of scattered glow sticks at arm's length. From a certain angle, they might appear to form a perfect circle, even though they're actually at varying depths. Studies analyzing galaxy velocities in the ring show some inconsistencies, with members moving at different speeds, fueling skepticism about a true physical connection. If this interpretation holds, the ring would be a spectacular cosmic coincidence, nothing more. But the opposing camp points to troubling anomalies. The ring's galaxies share uncanny similarities in age and chemical composition, as if cut from the same celestial cloth. Even more compelling is the discovery of faint stellar bridges, streams of stars connecting some ring members, suggesting gravitational interactions that wouldn't exist if they were unrelated objects at random distances. Computer simulations add weight to this view, showing how such structures could form through rare galaxy tsunamis, where clusters collide in just the right way to send galaxies rippling outward in orderly waves. Then there's the wildcard theory. The ring might be a fossil imprint of the early universe. Some researchers propose it's the aftermath of a long-ago encounter with a dark matter substructure, an invisible cosmic wake that herded galaxies into this improbable formation. Others speculate it could be evidence of large-scale quantum fluctuations frozen into the fabric of space during the Big Bang, a primordial fingerprint magnified to galactic scales. Whatever the truth, the implications are profound. If the ring is real, it suggests the universe can self-organize in ways we've never anticipated, potentially rewriting the rules of galactic evolution. If it's an illusion, it forces us to confront how easily even our most advanced observations can deceive us. Every new telescope trained on this enigmatic circle brings us closer to answers, or deeper into the cosmic unknown. In the crowded galactic metropolis of the Virgo Supercluster, astronomers recently spotted something that defies all expectations. A supermassive black hole racing through intergalactic space at breakneck speeds, leaving a glittering trail of newborn stars in its wake. This cosmic fugitive, detected in Galaxy 3C186, appears to have been violently ejected from its home, an event so energetically extreme it challenges our understanding of how black holes interact with their surroundings. What makes this runaway so astonishing is the trail it's carving, a narrow corridor of young, blue stars stretching over 200,000 light-years, like celestial breadcrumbs marking its path. Supermassive black holes typically anchor galaxies, sitting motionless at their cores. The idea of one being flung outward with enough force to escape its galaxy entirely was once considered nearly impossible. Yet here it is, barreling through the void at roughly 4.5 million miles per hour, fast enough to travel from Earth to the Moon in under 3 minutes. So how does a billion solar mass black hole get evicted from its own galaxy? The leading theory involves a cosmic game of gravitational pinball. When two galaxies merge, their central black holes eventually spiral toward each other, locked in a deadly dance. If a third black hole enters the mix, perhaps from yet another merging galaxy, the intricate three-body interaction can fling one of them outward like a slingshot. Computer simulations show these chaotic encounters can generate enough recoil to overcome even a galaxy's immense gravitational pull, launching the black hole into intergalactic exile. But the real marvel isn't just the ejection, it's the star-forming wake behind it. As the black hole plows through surrounding gas clouds, its immense gravity compresses the material, triggering bursts of star formation in its path. It's like a cosmic plow turning interstellar soil into stellar seedlings. This phenomenon, called shock-induced star formation, was predicted but never observed on such a spectacular scale until now. The Runaways Trail glows with the light of millions of young stars, each cluster a timestamp marking where the black hole passed through, yet mysteries remain. Why hasn't the black hole's accretion disk, the swirling ring of doomed matter that feeds it, disrupted during this violent journey? Some observations suggest it's still actively consuming gas, glowing brightly enough to outshine entire galaxies. Others argue the star-forming wake might actually be tidal debris, stellar material ripped from the original galaxy during the ejection. The implications ripple far beyond one rogue black hole. If these events are more common than we thought, they could explain why some galaxies appear to lack central supermassive black holes altogether. They might also seed interstellar space with wandering behemoths invisible until they interact with new gas clouds or pass too close to stars. Some theorists even speculate that early in the universe's history, such runaways could have played a role in distributing heavy elements across vast cosmic distances. What's certain is that this discovery shatters assumptions about how black holes behave. No longer can we think of them as stationary giants. They're dynamic, unpredictable, and capable of reshaping the cosmos in ways we're only beginning to understand. As telescopes grow more advanced, who knows how many more of these celestial outlaws we'll find streaking through the darkness, rewriting the rules of galactic evolution with every light year they travel. Between the brilliant galaxies of the Virgo Supercluster, darkness isn't quite as empty as it seems. A ghostly luminescence permeates the voids, an ethereal glow called Intracluster Light, so faint it took decades for astronomers to confirm its existence. This cosmic twilight comes from billions of orphaned stars, cast adrift by galactic collisions and now floating freely in the abyss. But here's what keeps scientists awake at night. Their distribution forms intricate, unpredictable patterns that our best simulations fail to replicate. To grasp how bizarre this is, picture throwing handfuls of sand into the wind. You'd expect the grains to scatter randomly. Instead, they arrange into precise shapes, spirals, tendrils, even vast clouds defying the chaos that should govern their dispersal. That's exactly what telescopes reveal in Virgo's Intracluster Light. The Hubble Space Telescope's deep exposures show delicate stellar streams woven between galaxies like a spiderweb, while Japan's Subaru telescope uncovered enormous stellar halos extending far beyond where models predicted they should end. The leading theory suggests this starlight comes from galactic cannibalism, smaller galaxies torn apart by larger neighbors, their stars scattered like crumbs from a cosmic feast. Computer simulations predict these stars should mostly accumulate near massive galaxies like Messier 87. Yet observations show they're spread unevenly, with mysterious concentrations in regions devoid of obvious parent galaxies. Some filaments stretch for millions of light years, tracing gravitational pathways we can't fully explain. Even stranger is the color of this lost light. Most intracluster stars appear unusually red, indicating they're ancient survivors from galaxies that met their demise billions of years ago. But recent discoveries by the Victor Blanco telescope in Chile found patches of unexpectedly blue stars mixed in, suggesting some regions experienced recent star formation. In the middle of nowhere, how could new stars ignite in the near-perfect vacuum between galaxies? Some astronomers propose rogue gas clouds compressed by the cluster's gravitational tides, while others wonder if dark matter's invisible hand is shaping these stellar nurseries. The implications ripple across cosmology. Intracluster Light was thought to map the supercluster's skeleton, revealing where dark matter's gravity is strongest. Yet Virgo's glow doesn't align with dark matter distributions inferred from galaxy motions. Either our dark matter models are incomplete or something else, perhaps unknown dynamical processes, is sculpting this stellar haze. Every new observation adds complexity, like the discovery of intracluster planetary nebulae blinking within the glow, their motions hinting at turbulent histories we're only beginning to unravel. What makes this phenomenon truly humbling is its scale. Conservative estimates suggest up to 10% of Virgo's total starlight exists in this diffuse form, enough stars to build 1,000 Milky Ways all adrift in the darkness. Their collective whisper challenges our assumptions about how clusters evolve, proving that even the emptiest corners of the cosmos hold stories waiting to be decoded. And until we can explain why these stars refuse to follow the rules, a fundamental piece of the supercluster's history remains written in light we're still learning to read. The Virgo Supercluster presents astronomers with a cosmic case of missing pieces where theory and observation clash in a way that shakes the foundations of modern cosmology. According to the widely accepted Lambda-CDM model, which describes how dark matter and ordinary matter structure the universe, massive galaxies like those in Virgo should be surrounded by swarms of dwarf galaxies like bees around a hive. Simulations predict hundreds should orbit each giant, yet we've only found a fraction of that number. This glaring gap, known as the missing satellite problem, isn't just a minor accounting error. It threatens to upend our understanding of galaxy formation itself. Take the Milky Way's neighbor, the Andromeda Galaxy, which resides in Virgo's outskirts. Lambda-CDM simulations suggest it should host at least 500 dwarf galaxies, based on the amount of dark matter in its halo. Yet fewer than 50 have been confirmed. The discrepancy grows even starker when we examine the Virgo cluster's core, where elliptical behemoths like Messier 87 loom. These titans should be drowning in satellites, yet their retinues are conspicuously sparse. It's as if the universe forgot to pack half its galactic luggage. So where did all the missing dwarfs go? One compelling explanation suggests we're simply not seeing them, not because they don't exist, but because they're too faint. Traditional surveys might miss ultra-dim galaxies shrouded in darkness. Their stars spread so thin they blend into the cosmic background. This idea gained traction with discoveries like Segway 1, a dwarf near the Milky Way containing 1,000 times more dark matter than visible stars. If most satellite galaxies resemble this ghostly archetype, our telescopes could be overlooking an invisible majority. But there's a catch. Even accounting for observational limitations, the numbers still don't add up. Some theorists argue the missing satellites might have been obliterated, torn apart by tidal forces during close encounters with their host galaxies. The Virgo cluster's violent environment supports this. Its crowded center acts like a gravitational blender, shredding fragile dwarfs over billions of years. Traces of this destruction are visible in stellar streams, rivers of orphaned stars winding through the cluster, the remains of galaxies that couldn't withstand the chaos. Then there's the nuclear option. What if dark matter behaves differently than we think? Alternative theories like warm dark matter propose particles that move fast enough to smooth out small-scale clumping, suppressing the formation of countless tiny galaxies. Others suggest interactions between dark matter and ordinary matter might have sterilized early dwarf galaxies, preventing stars from forming in the first place. These ideas remain controversial, but they highlight how deeply the missing satellite problem cuts into cosmological orthodoxy. The stakes couldn't be higher. If Lambda-CDM is correct, we're facing a monumental challenge in detecting the universe's faintest structures. If it's wrong, we might need to rewrite the rules governing cosmic evolution. New telescopes like the Vera Rubin Observatory are poised to tip the scales, scanning Virgo's depths for previously invisible dwarfs. Every new discovery, or lack thereof, brings us closer to solving one of astrophysics' most persistent puzzles. Until then, the missing satellites stand as silent witnesses to the gaps in our cosmic ledger, reminding us how much we still have left to find. Among the countless dwarf galaxies scattered across the Virgo Supercluster, a peculiar group stands out, not for their small size, but for being suspiciously oversized. These cosmic oddballs, dubbed ultra-massive dwarfs, flout the standard galactic rulebook, packing far more stars and dark matter than conventional models predict for their class. It's like discovering a population of domesticated cats the size of grizzly bears. Their very existence forces us to question what we thought we knew about galaxy growth. Take the striking example of VCC 128, a so-called dwarf galaxy in the Virgo cluster that shouldn't be nearly as hefty as it is. While typical dwarfs contain perhaps a billion stars at most, this behemoth harbors closer to 10 billion, comparable to some spiral galaxies, yet lacking their elegant structure. Even more confounding is its dark matter halo. Measurements suggest it outweighs the Milky Ways by a significant margin. How did a galaxy of this size fail to evolve into a grand spiral or elliptical like its neighbors? The answer might lie in an evolutionary dead end, a cosmic quirk that allowed it to balloon in mass while stunting its structural development. One prevailing theory points to a history of galactic cannibalism. Unlike solitary dwarfs that evolve in isolation, these overgrown anomalies might have gorged on smaller galaxies, piling up stars and dark matter without triggering the internal processes that drive larger galaxies to form disks or bulges. Supporting this idea are observations of disturbed stellar distributions and multiple distinct star populations within some ultra-massive dwarfs, telltale signs of past mergers. Yet this explanation hits a snag when we consider the sheer number of these outliers in Virgo. If mergers were the sole culprit, we'd expect fewer of them, given how precisely the conditions would need to align for a dwarf to feast repeatedly without being consumed itself by a larger galaxy. An alternative explanation dives into the realm of dark matter physics. Perhaps these dwarfs formed within unusually dense pockets of dark matter in the early universe, their growth stunted when reionization, the epoch when the first stars flooded the cosmos with ultraviolet light, stripped away their gas before they could mature further. This would leave them stranded in a kind of celestial puberty, massive yet underdeveloped. Intriguingly, some ultra-massive dwarfs show chemical fingerprints matching this scenario, ancient stars with minimal heavy elements, suggesting their star formation was indeed truncated early. But the plot thickens when we examine their distribution. These oversized dwarfs aren't randomly scattered, they cluster along the fringes of the Virgo Supercluster's most massive galaxies, like moths circling a flame. This peculiar positioning hints at another possibility. They might be the stripped cores of once larger galaxies, their outer layers torn away by violent encounters. Imagine a peach pit left behind after the fruit is eaten. The dense core remains, deceptively massive for its size. Some of Virgo's ultra-massive dwarfs exhibit precisely this signature, compact centers with star motions suggesting they're the remnants of much grander structures. What makes this mystery particularly tantalizing is its implications for cosmology. If these galaxies formed through unique pathways, they could represent an entirely separate class of objects, one our current classification systems don't account for. Their very presence challenges the standard hierarchical model of galaxy formation, where small structures merge to build larger ones. Here, we seem to have galaxies that grew massive yet stayed stunted, defying the typical growth sequence. As telescopes probe deeper into Virgo's dwarf population, each new discovery adds complexity to the puzzle. Some ultra-massive dwarfs host active black holes, a feature thought impossible for their size class. Others show signs of recent star formation, contradicting the notion that they're frozen relics of the early universe. With every anomaly catalogued, it becomes clearer that these cosmic misfits aren't exceptions, they're evidence of a richer, more varied galactic ecosystem than our textbooks ever anticipated. And until we understand their true nature, they'll remain a glaring reminder of how much we still have to learn about the universe's building blocks. Deep within the heart of the Virgo cluster, astronomers have stumbled upon something that shouldn't exist: massive walls of intracluster gas colder than the surrounding plasma by tens of millions of degrees. These cosmic cold fronts slice through the superheated medium like ghostly blades, defying everything we know about how energy behaves in galaxy clusters. Imagine opening an oven door expecting a blast of heat, only to find icy gusts rushing out instead. That's the level of paradox we're dealing with here. The intracluster medium, a soup of ionized gas filling the space between galaxies, is typically scorching hot, heated to over 10 million degrees by shock waves from galactic collisions and supernova explosions. Theory predicts this plasma should gradually smooth out over time, like steam dispersing in a sauna. Yet X-ray telescopes like Chandra reveal something utterly different: razor-thin boundaries where temperatures plummet abruptly, some stretching over 50,000 light-years. These structures aren't just anomalies, they're cosmic refrigerators operating in the middle of a furnace. How do these cold fronts survive in an environment where they should vanish in seconds? The leading explanation involves dark matter's invisible scaffolding. As galaxies plow through the cluster, their dark matter halos may act like cosmic plows, dragging cooler gas from their wakes and shearing it into coherent sheets. It's akin to stirring a cup of hot coffee with an ice cube. The surrounding liquid stays hot, but the cube's surface remains frigid far longer than expected. Some of these fronts even show intricate spiral patterns, suggesting they're relics of ancient collisions where gas was slingshot outward and then frozen in place by the cluster's magnetic fields. But the mystery deepens when we examine their longevity. Simulations show these structures should dissipate within 100 million years, yet many appear billions of years old. One particularly striking cold front near Messier 87 has maintained its sharp edge for at least 5 billion years, almost as old as our solar system. This endurance hints at unknown stabilization mechanisms, possibly involving magnetic fields woven so tightly they act like insulation, or subtle turbulence that somehow counteracts heat diffusion. Then there's the puzzle of their energy budget. The temperature drops across these fronts are so extreme, they imply energy is being siphoned away at scales that challenge conventional physics. Some researchers speculate they might be cosmic heat sinks, channeling thermal energy into particle acceleration or gravitational waves. Others propose they're markers of large-scale plasma instabilities, a phenomenon well known in fusion reactors but never observed on galactic scales until now. What makes these cold fronts more than just a curiosity is their potential to rewrite our understanding of galaxy clusters. They're not passive cauldrons of hot gas, but dynamic ecosystems where energy flows in ways we're only beginning to map. Every new observation peels back another layer, revealing a universe where even the most chaotic environments can harbor pockets of unexpected order, and where the rules of thermodynamics might need a cosmic-sized revision. Suspended in the vastness of the Virgo Supercluster, Hogs Object glows like a celestial bullseye, a perfect ring of young blue stars encircling an ancient golden core, with nothing but darkness stretching between them. This bizarre galaxy, discovered accidentally in 1950 by astronomer Art Hogue, defies every conventional model of galactic evolution. Most galaxies fall into familiar categories: spirals with winding arms, ellipticals like fuzzy blobs, or irregulars with chaotic shapes. Hogs Object belongs to none of these. It's a cosmic oddity so rare, fewer than one in every 10,000 galaxies resembles it, and its formation remains one of the most heated debates in astrophysics. At first glance, the structure seems impossibly delicate. The outer ring, spanning about 120,000 light-years, sparkles with clusters of stars less than 3 billion years old, relatively youthful by cosmic standards. Meanwhile, the central core contains elderly red stars nearly twice as old, with no visible spiral arms or dust lanes connecting the two regions. It's as if someone carved out the center of a galaxy and replaced the missing parts with a perfectly symmetrical halo of starlight. The most puzzling feature, the gap between the core and the ring, spans a staggering 75,000 light-years of near-total emptiness, a void devoid of the gas or stars that should logically bridge these components. How does such a structure arise without collapsing into chaos? One leading theory suggests a galactic collision, an intruder galaxy piercing the heart of what was once a normal spiral, its gravitational shockwave compressing interstellar gas into a star-forming ring. This resonance hypothesis draws parallels with the Cartwheel Galaxy, another ringed structure known to have formed from a direct impact, but Hogs Object presents problems. The core shows no signs of the violent disruption such an encounter would leave behind, and no obvious culprit galaxy lurks nearby to blame for the damage. An alternative explanation posits an extreme version of secular evolution, where internal instabilities in a rotating galaxy redistribute gas outward over billions of years, eventually triggering ring formation. Proponents point to faint outer rings observed in some barred spirals as evidence this process occurs on smaller scales. Yet Hogs' ring is far more pronounced than these examples, and simulations struggle to replicate its stark core ring separation without invoking outside interference. The galaxy's nearly perfect circular symmetry only deepens the mystery. Natural dynamical processes tend to produce lopsided or fragmented rings, not pristine halos. Then there's the wild-card scenario. Hogs Object might be the aftermath of an ancient, peanut-shaped galactic merger, where two similarly sized galaxies collided head-on, their stars settling into stable orbital planes that created the ring-core divide. Recent observations revealing a subtle second ring of older stars just outside the bright blue main ring lend credence to this idea, suggesting multiple epochs of formation. But critics argue the probabilities don't add up. Such mergers typically produce elliptical galaxies, not pinwheels of starlight. What makes Hogs Object especially tantalizing is its potential to rewrite galactic physics. If the ring formed without a collision, it implies galaxies can self-organize into radically different structures than our models predict. If a collision did occur, the lack of visible debris challenges our understanding of galactic interactions. Even more perplexing are the handful of other Hogue-type galaxies discovered since, each with slight variations that resist a one-size-fits-all explanation. Some display multiple concentric rings like tree rings, while others have warped or incomplete halos. This diversity suggests ring galaxies might emerge from several different pathways, making Hogs Object less an outlier and more a pioneer in a poorly understood class of celestial objects. Telescopes like Hubble and James Webb continue probing its secrets, analyzing stellar populations and hunting for faint traces of past violence. Every new image reveals subtle details, clumps of star formation in the ring, faint dust lanes near the core that keep theorists debating. For now, this cosmic enigma floats silently in Virgo's depths, a reminder that the universe often crafts its most beautiful objects through processes we've yet to comprehend. Winding through the Virgo cluster like a celestial serpent, the Virgo stellar stream isn't just another ribbon of starlight, it's a cosmic crime scene, the lingering evidence of a galactic murder mystery. This river of stars, stretching nearly 30 degrees across the sky, moves with eerie synchrony, as if bound by the ghostly fingerprint of whatever catastrophe forged it. Most stellar streams trace back to globular clusters or dwarf galaxies torn apart by gravity, but the Virgo stream refuses to fit the mold. Its stars are too metal-rich, their chemistry too evolved, suggesting origins far grander than the typical sacrificial dwarf galaxy. The puzzle begins with its sheer scale. While most tidal streams wrap tightly around their host galaxies, this one arcs boldly through intergalactic space, threading between massive cluster members like Messier 87 and Messier 89. Its trajectory implies an orbit tilted dramatically from the cluster's plane, an oddity that hints at a violent past. Some researchers propose it's the shredded remains of a once substantial spiral galaxy, perhaps as massive as the small Magellanic Cloud that strayed too close to the cluster's gravitational jaws. Computer simulations show such a galaxy could be stretched into a stream over billions of years, its stars scattering like crumbs along a gravitational freeway. Yet contradictions emerge when examining the stars themselves. Unlike the homogeneous populations expected from a single disrupted galaxy, the stream contains multiple stellar families with distinct ages and chemical compositions. This finding has birthed a radical theory. The Virgo stream might not be one casualty but several, a cosmic amalgam of multiple galaxies shredded and braided together by the cluster's tides. Imagine throwing handfuls of confetti into a whirlpool. The colors blend, but under scrutiny, you'd spot distinct batches from different sources. Advanced spectroscopic surveys have indeed detected at least 3 stellar subgroups within the stream, each with unique elemental signatures pointing to separate birthplaces. Even stranger is the stream's apparent lack of dark matter. When astronomers measured stellar motions to estimate the original galaxy's mass, the numbers suggested surprisingly little invisible scaffolding, unusual for galaxies of its presumed size. One explanation posits that the cluster's tides stripped not just stars but dark matter first, leaving behind a naked stream of visible material. Others argue the progenitor might have been a rare dark matter-deficient galaxy to begin with, adding another layer to the enigma. The most tantalizing clue lies in the stream's surroundings. Unlike the isolated tendrils seen around our Milky Way, this structure is embedded in Virgo's intracluster haze, that diffuse glow of orphaned stars mentioned earlier. Some astronomers believe the two phenomena are connected, with the stream representing a denser current within a broader river of intracluster stars. If true, it could mean we're seeing a snapshot of hierarchical stripping. First, galaxies lose their outer halos to form the Intracluster Light, then their cores are shredded into prominent streams like this one. New telescopes are bringing this cold case back to life. The Vera Rubin Observatory's upcoming deep surveys may reveal fainter extensions of the stream, potentially tracing its full orbital history. Meanwhile, the James Webb Space Telescope is analyzing individual stars for chemical tags that could pinpoint their birth galaxies. Every new dataset peels back another layer, but the central question lingers: was this stream forged by a single tragic encounter, or does it chronicle the cluster's gradual digestion of an entire galactic family? For now, the Virgo stream flows silently through the cosmic dark, its stars whispering fragments of a story we're still learning to decode. The Virgo Supercluster may harbor galaxies we can barely see, not because they're faint, but because they're made of something far stranger. Meet Virgo 21, a celestial phantom detected not by its starlight, but by the radio whispers of its hydrogen gas. This so-called dark galaxy appears to lack almost all visible matter, its sparse gas clouds orbiting nothingness as if tugged by an unseen cosmic hand. If confirmed, objects like this could rewrite the galactic playbook, proving entire galaxies can exist without the stars and dust we consider essential. Yet decades after its discovery, debate still rages. Is this a true dark matter-dominated galaxy, or just a cosmic mirage? The evidence for Virgo 21's existence comes from a celestial game of connect the dots. Radio telescopes picked up clouds of neutral hydrogen drifting near the famous galaxy Messier 89 gas, moving too swiftly to be explained by visible matter alone. The velocities suggested 600 times more mass than could be accounted for by the scant gas detected, pointing to a dark matter halo massive enough to host a Milky Way-sized galaxy. Stranger still, the gas showed no signs of tidal disruption, ruling out the usual explanation of debris from galactic collisions. It behaved like a cohesive structure quietly spinning in the void. Skeptics counter that we might be misreading the cosmic tea leaves. Some argue Virgo 21 could be a high-velocity cloud, a rogue intergalactic gas blob ejected during an ancient galactic encounter. Others propose it's the remnant of a failed galaxy, a clump of gas that never sparked star formation due to some primordial quirk. The most striking alternative came from observations with the Hubble Space Telescope, which revealed faint stellar streams near the gas's location. This fueled theories that Virgo 21 isn't a galaxy at all, but debris from a past collision between Messier 89 and another galaxy. Its dark matter signal merely an illusion created by our viewing angle. Yet the plot thickens when we examine similar candidates elsewhere in Virgo. Objects like Dragonfly 44, a galaxy with the mass of the Milky Way, but only 1% of its stars, hint that dark matter-dominated galaxies might not be rare flukes, but members of an entire hidden class. Some theorists suggest these could be primordial galaxies, frozen in an early state of evolution where dark matter overwhelmed normal matter. Others propose they're the remnants of galaxies stripped bare by cluster tides, their stars ripped away while their dark matter halos endured. What makes this debate pivotal is its implications for cosmology. If dark galaxies exist in numbers, they could solve lingering mysteries like why simulations predict more small galaxies than we observe. Perhaps we've been missing them because they're effectively invisible. Alternatively, if Virgo 21 and its kin prove illusory, we might need to rethink how gas behaves in extreme environments, or even how we measure dark matter's distribution. Advanced telescopes are finally bringing answers within reach. The square-kilometer array's unprecedented radio sensitivity could soon detect similar objects across Virgo, while James Webb's infrared eyes might spot the faintest stars hiding in these dark realms. Whatever the truth, these ghostly candidates remind us that the universe still holds entire categories of objects we've scarcely begun to imagine, galaxies not of stars and dust, but of shadow and mystery. The Virgo cluster holds another cosmic accounting error this time, involving the very building blocks of stars, planets, and even our own bodies. According to the universe's standard recipe, only about 5% of its total mass should be baryonic matter, the protons, neutrons, and electrons that make up everything we can see. The rest dark matter and dark energy, but when astronomers tally up the Virgo cluster's observable baryon stars, gas, dust, they come up shockingly short. Nearly half are missing, and their disappearance hints at gaps in our understanding of how matter cycles through the cosmos on the grandest scales. This cosmic vanish act isn't just a problem for Virgo. Across the universe, clusters seem to be missing baryons compared to predictions based on the cosmic microwave background, the afterglow of the Big Bang that reveals the universe's original matter distribution. But Virgo, being our nearest massive cluster, offers the clearest view of where this accounting might be going wrong. The leading suspect, intergalactic space itself. Hot, diffuse gas between galaxies known as the warm-hot intergalactic medium, or WIM, could be hiding vast reservoirs of baryons. This gas is so tenuous it barely emits light, making it nearly invisible to most telescopes. Here's where things get strange. When scientists used X-ray observatories like Chandra to map the Virgo cluster's WIM, they found some of the missing matter, but not nearly enough. The gas was there, just not in the quantities needed to balance the books. Some theorists suggest the baryons might have been ejected entirely from the cluster during its violent formation, flung into the cosmic voids beyond by powerful shockwaves from colliding galaxies. Others propose they've condensed into an unseen population of cold, dark clouds, or even been locked away in primordial black holes formed in the universe's first seconds. Then there's the dark matter connection. If baryons and dark matter interact in ways we don't yet understand, perhaps through some exotic force, the missing matter could be hidden in plain sight, woven into dark matter halos in forms we can't detect. Alternatively, the universe's expansion might have stretched and dispersed baryons so thinly that they've effectively vanished from our observational reach. The stakes of this mystery couldn't be higher. Baryons aren't just cosmic placeholders, they're the raw material for every star, every planet, every living thing. If we can't account for them, we're missing fundamental chapters in the story of how structure emerges from chaos. New tools like the upcoming Athena X-ray Observatory aim to hunt for these elusive baryons by detecting their faint fingerprints in intergalactic space. Until then, the Virgo cluster's missing matter remains one of cosmology's most persistent open cases, a silent reminder that even the ingredients we think we know best can still slip through our fingers. Barreling through the Virgo cluster at nearly 450 kilometers per second, Messier 86 isn't just moving, it's fleeing. This giant elliptical galaxy's trajectory stands out like a rogue wave in a calm sea, charging in the opposite direction of most cluster members. Such reckless cosmic speed should have consequences: galactic collisions, violent stripping of gas, or at the very least a visible shockwave in its wake. Yet Messier 86 defies expectations, maintaining its structure while hurtling through one of the densest regions of intergalactic space. This anomaly isn't just about raw velocity. It's a fundamental challenge to how we understand galaxies navigate their supercluster home. What makes this motion so perplexing is its context. Galaxies in clusters typically follow the gravitational flow, orbiting the common center of mass like bees around a hive. Messier 86, however, appears to be going against traffic, an observation that initially had astronomers questioning their measurements. Confirmed through decades of radio telescope data and Hubble's precise velocity readings, its retrograde movement suggests something extraordinary must have set it in motion. The leading theory, a close encounter with the cluster's true heavyweight, Messier 87, whose immense gravity could have slingshotted Messier 86 outward in a cosmic game of pinball. But the plot thickens when we examine the galaxy's physical state. High-speed journeys through clusters usually leave obvious scars. Galaxies get stretched, their gas torn away by the intracluster medium in a process called ram pressure stripping. Strangely, Messier 86 shows only mild disruption, with pockets of gas still intact despite its breakneck pace. This resilience hints at an invisible shield, perhaps an unusually dense dark matter halo absorbing the brunt of the intergalactic onslaught. X-ray observations reveal another twist. The galaxy drags a faint tail of hot gas, not behind it as expected, but curved slightly to one side, suggesting its trajectory might be even more complex than we've mapped. Alternative explanations push the boundaries of known physics. Some researchers propose Messier 86 isn't a native cluster member at all, but an interloper captured from a passing filament of the cosmic web, its momentum preserved from an ancient gravitational tug of war. Others speculate that the galaxy's motion could be influenced by large-scale dark matter currents, flows of invisible matter sculpting paths through the supercluster like underwater rivers guiding a submarine. The most radical theories even suggest local variations in dark energy density might be at play, creating pockets where the rules of galactic motion subtly shift. The implications ripple far beyond one rogue galaxy. If Messier 86's movement stems from conventional dynamics, it would mean galaxy clusters are far more chaotic than our simulations predict, with close encounters routinely flinging giants off course. If darker, more exotic forces are responsible, it could hint at gaps in our understanding of gravity itself. Every new observation adds nuance, like the recent discovery of faint stellar streams around Messier 86, possible evidence of smaller galaxies torn apart during its high-speed journey. Upcoming surveys with the Vera Rubin Observatory aim to trace its path in greater detail, potentially uncovering clues about the forces that set it in motion. For now, this galactic rebel continues its solitary charge against the current, a silent testament to the fact that even in the well-mapped territories of our supercluster, the cosmos still has surprises up its sleeve. The Virgo cluster hides an invisible storm, a vast, crackling sea of radio waves spanning millions of light-years, so faint it eluded detection until the era of modern radio telescopes. This cosmic phenomenon, known as the Virgo cluster radio halo, isn't tied to any single galaxy or explosion. Instead, it blankets the entire cluster like static from an unseen cosmic broadcaster, its signal whispering secrets about forces we're only beginning to comprehend. What makes this halo so baffling isn't just its scale. It's the fact that according to conventional physics, it shouldn't exist at all. At the heart of the mystery lies a fundamental question. How can such diffuse radio emission persist in a relatively quiet cluster like Virgo? These halos typically form in the aftermath of violent galactic collisions, where shockwaves accelerate particles to near light speeds, creating synchrotron radiation, the same process that lights up pulsars and quasars. But Virgo's halo defies expectations. Unlike the turbulent merger clusters where these structures usually appear, Virgo is considered moderately calm, with no recent history of giant collisions. Its galaxies drift in a more orderly fashion, yet the halo's presence suggests hidden turmoil simmering beneath the surface. When astronomers first mapped the halo's intricate tendrils using arrays like the Very Large Array and LOFAR, they uncovered something even stranger. The radio glow isn't smooth but patchy, with filaments and voids tracing invisible magnetic fields woven through the cluster. These fields are thought to act like cosmic accelerators, pumping energy into electrons over eons. Yet simulations struggle to explain how particles could maintain such high energies across such vast distances without constant replenishment. Some regions of the halo appear to correlate with faint X-ray emitting gas, hinting at subtle interactions between the intracluster medium and relativistic particles, a dance of energy transfer we've yet to fully decode. One radical theory proposes that the halo might be fueled by the cumulative effect of countless smaller events, supernova in dwarf galaxies, jets from active black holes, or even decaying dark matter particles. Another suggests that Virgo's calm is an illusion, and the cluster is still reverberating from ancient collisions we can no longer directly see. Supporting this idea are faint distortions in the distribution of galaxies, subtle evidence of past mergers that might have injected enough turbulence to seed the halo. The implications stretch far beyond Virgo. If we can't explain how such a halo persists in a relaxed cluster, our models of cosmic ray acceleration and magnetic field evolution might be missing critical physics. Some researchers speculate the answer could involve unknown plasma instabilities or even exotic particle interactions between dark matter and the intracluster gas. Upcoming radio telescopes like the Square Kilometre Array promise to peel back another layer, mapping the halo's structure in unprecedented detail. Until then, this invisible electromagnetic shroud remains one of the supercluster's most electrifying puzzles, a reminder that even the spaces between galaxies hum with unseen energy waiting to be understood. Scattered like sapphire droplets on black velvet, the blue drops of Virgo glow with an otherworldly intensity, isolated pockets of star formation floating in the cosmic void, untethered from any parent galaxy. These celestial anomalies shouldn't exist under standard galactic models, where stars typically form within the dense gas clouds of galaxies. Yet here they are, blazing with the light of newborn stars in regions so remote, their nearest galactic neighbors lie hundreds of thousands of light-years away. Their very presence forces astronomers to reconsider what ignites the fires of star birth in the deepest, emptiest reaches of intergalactic space. One of the most striking examples lurks near the galaxy Messier 99, where Hubble spotted a cluster of massive blue stars adrift in nothingness. These aren't just any stars, they're O-types, the hottest and most short-lived stellar behemoths, burning through their fuel in mere millions of years. Their isolation raises a glaring question. How did enough gas accumulate in intergalactic space to birth such demanding stars without the gravitational crutch of a galaxy? The leading theory points to tidal dwarf formation, where galactic collisions fling out massive streams of gas that later collapse under their own gravity. But there's a problem. Many of these blue drops show no obvious connection to nearby galaxy interactions. They're pristine environments devoid of the telltale debris expected from such violent origins. Alternative explanations venture into uncharted astrophysical territory. Some researchers propose these regions might be seeded by dark galaxies, invisible halos of dark matter whose gravity corrals stray gas into star-forming pockets without ever forming stars themselves. Others suggest cosmic rays or intergalactic magnetic fields could be triggering localized collapses in the diffuse hydrogen fog that permeates galaxy clusters. Then there's the radical idea that these drops are the aftermath of cold accretion, where filaments of the cosmic web funnel gas directly into dense nodes, bypassing galaxies entirely, a process thought to have been important in the early universe but rarely observed today. The intrigue deepens when examining their life cycles. Unlike galactic star clusters, which often disperse over time, these intergalactic formations appear strangely stable. Spectroscopic analyses reveal some are enveloped in faint hydrogen halos, acting like cosmic incubators that protect their stellar nurseries from the evaporating effects of the intracluster medium. Others show evidence of multiple generations of stars, suggesting prolonged periods of star formation in what should be a gas-starved environment. It's as if these regions have tapped into a hidden reservoir of fuel, defying the harsh conditions of intergalactic space. What makes the blue drops more than just cosmic curiosities is their potential to rewrite the story of star formation. If stars can ignite and thrive in the void, it implies the universe is far more prolific at creating stellar factories than we ever imagined. Upcoming telescopes like the James Webb Space Telescope are poised to hunt for fainter, older examples, potentially revealing whether these drops are rare accidents or the visible tips of a vast, unseen archipelago of intergalactic stars. For now, they remain luminous enigmas, a proof that even in the deepest emptiness, the cosmos finds ways to spark new light. At the heart of the Virgo cluster, where galaxies swarm in their densest numbers, a cosmic contradiction unfolds. Here, amid the searing heat of intergalactic gas, physics demands that something impossible should be happening: rivers of cooling plasma collapsing inward to feed the supermassive black holes at the cluster's core. This process, called a cooling flow, is expected in massive galaxy clusters where gas at the center radiates away heat and should steadily sink toward the central galaxies. Yet Virgo defies this universal script. Its core remains strangely lukewarm, as if some unseen cosmic thermostat is preventing the expected cooling cascade, and the implications shake the foundations of how we understand these galactic metropolises. Think of a galaxy cluster as a sprawling city where the downtown core should naturally attract the most activity. The intracluster gas, a superheated plasma filling the space between galaxies, loses energy as it emits X-rays. Like steam condensing on a cold window, this cooling gas should then flow inward toward the cluster's gravitational center, fueling bursts of star formation and feeding voracious supermassive black holes. For decades, astronomers observed this exact behavior in distant clusters, but when they pointed their telescopes at Virgo, the closest massive cluster to Earth, the predicted downpour of cooling gas simply wasn't there. The central galaxy, Messier 87, sits in a puzzling state of semi-starvation, its legendary black hole active but not nearly as gluttonous as models suggest it should be. One explanation points to a phenomenon called AGN feedback, a cosmic balancing act where the central black hole's outbursts reheat the cooling gas, preventing it from settling. As gas begins to condense toward Messier 87, the supermassive black hole might unleash jets of energy, stirring the surrounding plasma like a spoon in a mug of hot coffee. Supporting this idea are the spectacular relativistic jets blasting from M87's core, along with faint bubbles of radio emission detected in the surrounding gas, telltale signs of past eruptions. But here's the catch: the energy from these outbursts doesn't perfectly match the missing cooling flow. The math leaves gaps, suggesting the black hole's tantrums alone can't fully explain the suppressed cooling. Another clue emerges from the cluster's dynamic history. Unlike some monolithic clusters, Virgo is still assembling itself, with galaxies streaming in a long cosmic filament. This ongoing construction might inject turbulence into the intracluster medium, keeping the gas too agitated to cool efficiently. Picture a whirlpool constantly disturbed by new currents. It never gets the chance to settle into a smooth spiral. X-ray observations reveal exactly this kind of chaotic motion in Virgo's core, with gas velocities varying unpredictably over scales of thousands of light years. Yet simulations show this turbulence should dissipate over time, leaving a clearer cooling signature than what we observe. The mystery deepens when we compare Virgo to other clusters. Some display cold fronts, sharp edges where gas temperatures plummet yet still exhibit cooling flows. Virgo has these cold fronts too, but they don't trigger the expected cooling cascade. This discrepancy hints at something unique about Virgo's environment. Perhaps its relatively low mass compared to giant clusters like Coma, or the specific way its central black hole interacts with surrounding gas is breaking the mold. Some theorists even speculate that dark matter's distribution in Virgo could play a role, its invisible scaffolding influencing gas flows in ways we haven't yet modeled. Perhaps the most radical possibility is that our understanding of plasma physics in these extreme environments is incomplete. The intracluster medium isn't just hot gas. It's a magnetized, weakly collisional plasma where particles interact over vast distances. Under these exotic conditions, heat might transfer through mechanisms we don't yet account for in our equations. Certain wave-particle interactions or large-scale magnetic fields could effectively insulate the core, slowing cooling without requiring constant reheating. Recent observations from NASA's Chandra X-ray Observatory found subtle temperature patterns in Virgo's gas that align poorly with standard cooling models, suggesting our textbooks might need revision. The implications extend far beyond one cluster. If we can't explain why Virgo resists cooling flows despite being the closest and best-studied massive cluster, our models for how all galaxy clusters evolve may contain critical blind spots. These celestial cities dominate the universe's large-scale structure, and their cooling behavior regulates star formation across cosmic time. Upcoming X-ray missions like XRISM and Athena aim to probe Virgo's gaseous heart with unprecedented precision, potentially revealing the missing pieces of this thermodynamic puzzle. Until then, Virgo's stubborn refusal to cool stands as a humbling reminder that even our closest cosmic neighbors still hold profound secrets. In the swirling dance of galaxies across the Virgo Supercluster, an eerie pattern emerges, one that defies the randomness we'd expect from billions of years of cosmic evolution. Astronomers have discovered that many Virgo galaxies spin in surprisingly similar directions, their rotational axes aligned like compass needles pointing toward some unseen force. This isn't just a fluke, it's a coordinated motion on scales so vast it hints at influences operating far beyond the boundaries of individual galaxies, something weaving order into the fabric of the cosmos itself. Typically, galaxies spin in random orientations, their rotations shaped by local conditions during their formation. But when researchers mapped the spin directions of hundreds of Virgo galaxies, they found clusters where neighbors were far more likely to share aligned axes than chance alone could explain. Some regions show galaxies spinning like gears in a cosmic clockwork, their disks parallel to one another across millions of light years. The probabilities of this happening naturally are astronomically low, like flipping a coin 1,000 times and getting heads 900 times in a row. So what could be behind this synchronized motion? One leading theory points to the cosmic web, the vast filamentary network of dark matter and gas that connects galaxies across the universe. As galaxies form along these filaments, their spins might inherit alignment from the primordial angular momentum of the gas flowing into them. Picture leaves caught in a river's current, all drifting in the same general direction. Computer simulations show this process can create weak correlations in spin, but nothing as pronounced as what we see in Virgo. The observed alignments are too strong, too precise, suggesting something else is at work. Another possibility involves tidal torque theory, the idea that galaxies can be twisted into alignment by the gravitational pull of nearby massive structures. Virgo's dense core, dominated by behemoths like Messier 87, could generate tidal forces strong enough to coax smaller galaxies into a shared orientation. Yet even this explanation struggles to account for alignments spanning such enormous distances. Some galaxies in these coherent spins lie too far apart to have influenced each other through gravity alone, unless dark matter interacts in ways we've yet to discover. Then there's the wild card, cosmological inflation. The alignments might be relics from the universe's infancy, imprinted when the cosmos was smaller than an atom. Quantum fluctuations during this exponential expansion could have seeded large-scale correlations in angular momentum, preserved across eons as galaxies formed. If true, these spin patterns could be fossilized whispers from the first moments of time, a hidden code written into the architecture of the cosmos. The implications are profound. If galaxy spins aren't random but instead shaped by forces operating at supercluster scales, it challenges our understanding of how cosmic structures influence one another. It also raises tantalizing questions about the nature of dark matter. Could its distribution or behavior be subtly orchestrating these alignments? Or does this phenomenon point towards something even more exotic, like undiscovered large-scale magnetic fields or remnants of a primordial spin field? As telescopes grow more advanced, astronomers are racing to map these alignments in greater detail, searching for patterns that might reveal their origins. Every new galaxy surveyed adds another piece to the puzzle, one that might ultimately rewrite our cosmic playbook. For now, these eerily synchronized spins stand as one of Virgo's most mesmerizing mysteries, a silent reminder that even in the vast chaos of the universe, hidden orders wait to be uncovered. Stretching between the galaxies of the Virgo Supercluster like cosmic bridges, vast filaments of dark matter and gas weave the largest structures in the known universe. These tendrils of the cosmic web are supposed to be stellar nurseries, highways of matter where gravity pulls galaxies together into glittering knots. Yet when astronomers mapped these filaments in detail, they encountered a baffling discrepancy. Entire stretches appear eerily empty, devoid of the galaxies that simulations insist should be there. It's as if we've found the blueprints for a bustling metropolis, only to arrive and discover half the buildings are missing. The heart of this puzzle lies in the mismatch between prediction and observation. Supercomputer simulations of cosmic evolution, based on our best understanding of dark matter and gravity, paint filaments as dense galactic thoroughfares. They should be studded with dwarf galaxies and star-forming regions, especially near intersections where multiple filaments converge. But when teams used telescopes like Hubble and Subaru to survey known filaments in Virgo, they found sprawling desert regions, some spanning tens of millions of light-years, where galaxy counts fell dramatically short. In places, the voids between galaxies were up to 5 times larger than models anticipated, leaving astronomers scrambling to explain the disparity. One leading theory suggests we're simply not seeing the full picture. These filaments might be packed with ultra-diffuse galaxies so faint they blend into the cosmic background. Supporting this idea are recent discoveries like the Hidden Giants project, where sensitive instruments detected previously invisible dwarf galaxies lurking in seemingly empty filaments. But even after accounting for these ghostly structures, the numbers don't fully reconcile. The missing galaxies aren't just dim, they're fundamentally absent, as if something prevented their formation altogether. Another explanation dives into the chaotic physics of filament environments. While these cosmic threads contain ample gas, their extreme low density might hinder galaxy formation. Gas clouds need to cool and condense to birth stars, but in filaments, particles are so spread out that gravitational collapse happens agonizingly slowly or not at all. Some researchers propose that cosmic rays or intergalactic magnetic fields could further disrupt this process, leaving gas stranded in a perpetual state of limbo. Observations from the Chandra X-ray Observatory reveal filaments peppered with failed galaxies, clumps of gas that glow faintly but never quite ignite into stellar factories. Then there's the dark matter wildcard. If dark matter interacts with itself or ordinary matter even slightly beyond gravity's pull, it could subtly alter how structures form within filaments. Certain theoretical models suggest dark matter particles might scatter off one another, smoothing out density fluctuations that would otherwise seed galaxies. This would explain why some filaments appear overheated, their gas too agitated to coalesce, a phenomenon detected in the Virgo cluster's outermost filaments, where gas temperatures defy expectations. But perhaps the most radical possibility is that these underpopulated filaments are relics of the early universe's quirks. Variations in the primordial density field imprinted during inflation might have created regions where matter was distributed just sparsely enough to delay galaxy formation. In this scenario, the empty stretches we see today aren't anomalies but time capsules, preserving a slower-paced alternative path of cosmic evolution. What makes this filament puzzle so critical is its implications for cosmology at large. If our simulations overpredict galaxy numbers, we might be missing key physics in how structures assemble. Alternatively, if the galaxies are there but hidden, it challenges our observational limits. Upcoming projects like the Euclid Space Telescope aim to map these filaments in unprecedented detail, hunting for the faintest galactic denizens. Until then, the supercluster's threadbare bridges remain a cosmic contradiction, a reminder that even our grandest models of the universe are works in progress, refined by the very voids they fail to explain. The Virgo Supercluster may be caught in a cosmic current, an inexplicable river of motion carrying countless galaxies toward some unseen horizon. Astronomers call this enigma the dark flow, a controversial phenomenon where entire clusters, including Virgo, appear to drift in unison toward a point beyond the observable universe. This isn't the familiar expansion of space, but something far stranger, a coordinated movement that hints at structures or forces so vast they lie beyond our cosmic horizon, tugging at everything we can see. Initial evidence emerged from studies of the cosmic microwave background, the afterglow of the Big Bang. Subtle distortions in this primordial light suggested clusters were moving at astonishing speeds, up to 1,000 kilometers per second, in the same general direction. These velocities shouldn't exist in a universe where matter is distributed evenly on large scales. The dark flow's proposed explanation, a gravitational anomaly of unimaginable scale, perhaps a supercluster of galaxies so massive its pull extends across cosmological distances, or even remnants of a pre-Big Bang structure imprinting its influence on our cosmos. Skeptics argue this could be an artifact of measurement errors or local dynamics. The Virgo cluster's motion, for instance, might blend with the great attractor's influence or reflect larger-scale flows within the Laniakea supercluster. Yet the persistence of these anomalous velocities in multiple independent studies keeps the debate alive. Some researchers propose the dark flow could stem from quantum fluctuations during inflation, the universe's explosive early growth, that left asymmetric imprints on matter distribution. Others speculate about parallel universes exerting gravitational leakage through higher dimensions, though such ideas remain firmly in theoretical territory. What makes this controversy so gripping is its implications. If real, the dark flow suggests our universe isn't just lopsided but interconnected with realms beyond our observational limits. Upcoming missions like the Euclid Space Telescope aim to map galaxy motions with unprecedented precision, potentially settling the argument. Until then, this cosmic undercurrent remains one of Virgo's most profound mysteries, a whisper that the universe's true shape might be far grander than we've dared to imagine. Among the countless mysteries of the Virgo Supercluster, one of the most puzzling shines in a spectrum invisible to human eyes, an unexplained flood of ultraviolet light radiating from the cluster's heart. This UV excess isn't just a minor anomaly, it's a cosmic glare so intense it challenges our understanding of how galaxies age and evolve. Normally, massive galaxy clusters like Virgo should glow primarily in X-rays from their scorching intracluster gas with a predictable amount of UV from young stars. But when astronomers aimed ultraviolet telescopes like Galex and Hubble at Virgo, they detected up to 30 times more UV emission than any conventional model could explain, a surplus equivalent to billions of missing stars somehow radiating in this elusive wavelength. At first, scientists suspected the culprit might be an overlooked population of hot, young stars, stellar outliers burning so fiercely they output most of their energy in UV. But when they scrutinized the cluster's galaxies, the numbers didn't add up. The required quantity of such stars would make Virgo's galaxies shine far brighter in visible light than they actually do. Another theory pointed to white dwarfs, the smoldering cores of dead stars, which can emit UV as they slowly cool. Yet even these stellar embers couldn't account for the sheer scale of the excess. The discrepancy forced astronomers to consider more exotic possibilities, perhaps a hidden population of stars stripped of their outer layers during galactic collisions, exposing their scorching hot interiors. Imagine a forest where every tree had its bark peeled away, leaving nothing but searing, naked trunks radiating intense heat. That's the kind of radical scenario researchers began contemplating. Then came the real curveball. Detailed spectral analysis revealed the UV light wasn't just slightly off, it carried a peculiar signature inconsistent with any known stellar process. Some wavelengths were suspiciously smooth, lacking the atomic absorption lines expected if stars were the source. This anomaly birthed a radical hypothesis. The excess might not come from stars at all, but from an entirely new form of radiative decay, perhaps from hypothetical particles like actions or sterile neutrinos interacting with the cluster's magnetic fields. Others proposed it could be the collective glow of countless rogue planets, ejected from their star systems and heated by intergalactic radiation to UV-emitting temperatures. The plot thickened when astronomers noticed the UV excess wasn't evenly distributed. It clustered around certain galaxies, particularly massive ellipticals like Messier 87, and correlated oddly with regions of high dark matter density. This tantalizing link led some theorists to suggest the UV might be a side effect of dark matter annihilation or decay, a process long predicted by particle physics but never directly observed. If true, Virgo's mysterious glow could be our first glimpse of dark matter's hidden interactions, shining not in the visible spectrum but in ultraviolet whispers. Yet challenges remain. Alternative explanations like shock-heated gas or unresolved quasars still lurk in the margins of plausibility. The upcoming UVEX mission, slated to map the sky in unprecedented ultraviolet detail, may finally settle the debate. Until then, Virgo's UV excess stands as a luminous enigma, a reminder that even the most studied corners of the cosmos can harbor light we don't yet understand, illuminating gaps in our knowledge as vividly as the mysteries themselves. From the ghostly whispers of dark matter to the blazing defiance of runaway black holes, the Virgo Supercluster has revealed itself as a cosmic hall of mirrors, where every answer reflects back a dozen new questions. These 25 mysteries aren't just gaps in a map, they're seismic tremors shaking the foundations of astrophysics. Take the missing satellites problem. How could our most sophisticated simulations predict hundreds of dwarf galaxies that simply aren't there? Or the ultra-diffuse galaxies clinging to existence like cobwebs in a hurricane, their delicate stars resisting annihilation against all odds. Even the supercluster's scaffolding defies logic, with dark matter filaments stretching into galaxy-starved voids and cold fronts slicing through million-degree plasma like cosmic refrigerators. Consider the implications of Hogs Object, a galaxy so perfectly ringed it looks designed by an unseen hand, or the great Attractor's gravitational siren call, pulling thousands of galaxies toward a point obscured by our own Milky Way. These aren't isolated puzzles, they're interlocking pieces of a grander enigma. When intracluster light glows where no stars should be, when galaxies spin in eerie synchrony across millions of light years, when invisible rivers of baryonic matter vanish without a trace, we're forced to confront the humbling truth that our cosmic playbook is missing entire chapters. What makes these mysteries so electrifying is their sheer audacity to exist. In an era where we've mapped the afterglow of the Big Bang and photographed black hole shadows, the Virgo Supercluster whispers that the universe still holds cards close to its chest. Perhaps dark matter isn't what we think. Perhaps gravity plays by different rules on cosmic scales. Or perhaps most thrilling of all, we're on the verge of discoveries that will rewrite physics itself. So here's your invitation to the greatest detective story in existence. Which of these cosmic riddles keeps you awake at night? Is it the phantom galaxies made only of dark matter, or the star-forming blue drops blooming in the void? Drop your thoughts below, and if you're craving more journeys to the edge of understanding, hit subscribe as we continue unraveling the universe's deepest secrets, one mind-bending mystery at a time. The cosmos is stranger than we imagined, and the next revelation is always just beyond the telescope's